So, gonna try out the whiteboard for the next couple of weeks. I mostly like it. The only thing that I don't like about it is that just because of my office setup, I can't get the camera to shoot like 90 degrees on. I'm gonna try to fix that maybe a little bit. There's slack in the cord, but I don't know how much slack I can get out. Okay. So today we are going to talk about pre-calculus recap, or sorry, not pre-calculus recap, vector calculus recap. And the reason is that unlike the conservation equations, the diffusion equation, and the wave equation, Laplace's equation is legitimately a two-space variable equation. There's no real way to make any sense of it if we want to consider one of the variables as being a time variable. It just doesn't make sense. That's what we might call an evolution equation. And if we have time, I'll explain that a little bit more. But the idea is we've got to have two space variables. Up until now, we've only had one space variables, though there are multi-space variables. Well, in fact, we'll look at one of them, multi-space variable versions of all of the equations that we've looked at. But the ones we've seen so far have had one space variable, so we've been able to avoid vector calculus, or I like it, so I guess it's bad. But now, when we're doing Laplace's equation, we have to do vector calculus. And even still, we're only going to be working in R2. So we're not going to be doing a lot of vector calculus, just some R2 stuff, which makes a lot of the formulas, it makes it, well, we can be a lot more explicit with our formulas than if we were dealing in Rn or something like that. Okay, so let's start with Green's theorem. So Green's theorem, the setup is the following. We have some domain, sorry, these are supposed to be connected. We have some domain omega. The curve that bounds it is called the boundary of omega. And we have a special symbol for it. So the boundary of omega this is called the boundary of omega. And I'm not going to say this explicitly probably ever again, but I'm going to assume that the boundary of omega, that this is nice. Okay, and what I mean by that is basically there's no points. It's a nice smooth curve that's bounding it. And Green's theorem starts with an integral along the outside of this boundary. So I have an integral like this, and I've got p dy minus q dx. Okay, so what's going on here? What do these different pieces mean? Well, this is the boundary of omega. That tells us the thing over which we are taking the integral. So we're taking the integral around the boundary of omega. So it's like a one-dimensional integral. It's a line integral. The circle here means that the curve that we're taking the integral over is a closed curve. In other words, it starts and ends at the same point. P is going to be a function in R2, but we're only looking at it along this curve right here. And similarly, Q is a curve in R2, Q is a function in R2, but we're only looking at it around this boundary. And the dy and dx, well, these are things that we integrate along the boundary, but it basically means we're just kind of looking at the y component or the x component. Now, practically speaking, how do we compute something like this? Well, from the definition, or so there's going to be Green's theorem, which we're going to go over. It's going to be one way to compute this. But if we don't use Green's theorem, another way we can compute this is the following. Let's say that r of t, let's say this is a vector parameterization for this curve. So let's say this is a vector parameterization for the curve, and let's say the parameter goes from a to b. So in other words, the r of t vector, or sorry, the r of a vector goes here, and then as we travel around the curve, it traces it out and ends back there at r of b. Okay. Then dx is equal to x dot, the derivative of x with respect to t, dt, and dy is equal to y dot, which is the derivative of y with respect to t. And so what this is, again, this is just a line integral. We're computing it from t equals a to b. So I'm going to evaluate p at the parameterization. So x of t, y of t. And then what is dy? dy is y dot dt. So this is going to be y dot of t dt. And then for the q integral, it's the integral from a to b, q of x of t, y of t, and then dx is x dot dt. Okay, now this integral, or both of these integrals here, this is just a normal integral from t going from a to b. It's just a regular Calc 1 integral. But it is how we compute this line integral here around the boundary. So let's look at a specific example here. Instead of this omega, let's say our omega is a disk of radius 1 centered at the origin. Let's say our omega is a disk of radius 1 centered at the origin. This is the x-axis, this is the y-axis. Okay, so if we come over here, our parameterization is going to be cosine t sine t. At least that's one parameterization of the unit circle. And our t values are going to go from 0 to 2 pi. Okay, so what's dx going to be? What are dx and dy going to be? Well, dx is going to be the derivative of cosine times dt. So that's going to be minus sine t dt. And what's dy? Well, dy is going to be the derivative of sine t, so cosine t dt. Okay, so if I come back up here to my integrals, let's see what I'm going to have going on here. Oh, I haven't told you what p, and I haven't given you p yet. So I will write over here p of xy is equal to x squared, and q of xy is equal to y. Okay, we're going to get to brush up some of our trig identities here. All right, so now what's the integral going to be? Well, this first integral, I'm integrating from t going from 0 to 2 pi. P is x squared. Okay, so x, along the parameterization, x is cosine. So I'm going to have cosine squared. Okay, dy is equal to cosine t. So dy is equal to cosine t. So this is going to be cosine t minus the next integral, the q integral. I'm going to have the integral going from 0 to 2 pi. What's q? Q of xy is y. Along the parameterization, y is sine t. So this is going to be sine t. And then what about dx? Dx is minus sine t. Okay, so this is going to be, the plus sign will come out here. So this will be sine t dt. Okay, just to point out what's going on here. This is p of x of t, y of t. This is dy. This is q of x of t, y of t. And then this whole part here is dx, though I put the minus sign out there, so I guess it's really minus dx. Okay, so let's compute this. Okay, now for this integral, this is the integral from 0 to 2 pi. Okay, so pause for a minute, see if you remember how to do this integral. Okay, so hopefully we'll get the same thing. So cosine squared, I can write this as 1 minus sine squared, and then cosine. Okay, this is a very good u sub integral. And then over here, I'm going to have the integral from 0 to 2 pi. I'm going to have the integral from 0 to 2 pi. I have sine squared. So sine squared, I'm going to have to use my my half angle or double angle identities, whatever they're called. This is going to be 1 minus cosine of 2t divided by 2 dt. Okay, so over here I'm going to do u sub. I'm going to say u is equal to sine t. And so what I have, this part is going to be 1 minus u squared. Cosine t dt, this is just equal to du. Now the bounds on the integral, I have to change those. So these are my t bounds. So if t is equal to 0 and u is equal to sine of t, u is going to be 0 here. On the top, if t is equal to 2 pi and u is equal to sine of t, the top bound is going to be sine of 2 pi, which is also 0. So this integral is 0. Then over here, I'm going to have the integral from 0 to 2 pi, 1/2 dt, minus the integral from 0 to 2 pi, cosine 2t over 2 dt. Okay, so this integral is 0. What about this integral? Well, if I do this integral, it's just going to be pi. It's 1/2 times 2 pi. So this is pi. Now, this integral, sorry, I forgot my 2 pi here. So this integral, cosine of 2t, the antiderivative is going to be sine of 2t. When you evaluate sine of 2t times a constant, but when you evaluate sine of 2t at both of those points, they're both going to be equal to 0. So that integral is equal to 0. So overall, this integral is equal to pi. Okay, I'm about to erase this, so copy anything down or pause it if you need to copy this down. I'm about to erase from here down, all the black stuff over there. Okay, so this is one way that we use to compute this line integral, but there's another way that you might remember called Green's theorem. Now, the form of Green's theorem that I'm going to give is slightly different than what you might ordinarily see, only because I'm doing p dy minus q dx, and oftentimes this is set up as q dx plus p dy or something like that. So it's going to look a little bit different. Like if you look at the Wikipedia page, it might look a little bit different, but it's actually not different if you just make the right identifications. Okay, that's just a warning. I'm using it this way because there's a reason I'm using it this way. The reason I'm using it this way is because I need to apply it later, and the thing that I'm going to be integrating has this form here. All right, so by Green's theorem, this is an integral over the boundary of omega. We can write this as an integral over omega itself. So we can write a boundary integral as an area integral, or a line integral as an area integral. And the integral is going to be the x derivative of p plus the y derivative of q, and then dA here. Okay, so dA is dx dy, it's the integrating in the plane thing. Okay, and I write with two integrals, even if we're not treating it as an iterated integral, and I will often write something like dx dy, even if we're not treating it as an iterated integral. Okay, so again, integral over the boundary, integral over the area. So notice here we're integrating the function, and over here we're integrating the derivative of the function. So this is very similar to the fundamental theorem of calculus. If I'm going from a to b, what do I know? I know that the integral from a to b of f prime of t dt is equal to f of b minus f of a. So here I'm doing something on the boundary. This is kind of what you might call an integral on the boundary. The boundary is just 2 points. I'm doing the integral on the boundary here. What am I doing here? I'm doing an integral over the domain itself, but I have a derivative. That's what I have up here. Integral over the boundary without a derivative. Integral over the domain with a derivative. Okay, so Green's theorem is just one of the many generalizations of the fundamental theorem of calculus to higher dimensions. Okay, so let's actually try to compute it. Let's try to compute this example using Green's theorem. So what are we going to have? So my domain is still going to be the ball, or the disk of radius 1, centered at the origin. This is true for all omega, okay, not just for the ball, but that's the example that we're going to use. Okay, so p of xy is x squared. The x derivative is 2x. Q is y. The y derivative of y is 1. And then we'll have dx dy. See, it's confusing how I've written it here because I don't have the bounds for x and y here. Okay, but I'm integrating over a circle. Let me just even emphasize this. I'm integrating over the disk or the ball of radius 1, centered at the origin. Okay, so how do I do this type of integral? I should be using polar integration. So this is also a good recap for polar integration, though I'm not really recapping anything. I'm just reminding you to look it up because we're going to be using it. So remember, for polar integrals, we have x is equal to r cosine theta, y is equal to r sine theta, and then dA or dx dy is equal to r dr d theta. So again, in most people's conventions, even though it's not precise, dx, dy, and dA kind of mean the same thing, except, well, anyways. Okay, so what are we doing over here? The theta will be going from 0 to 2 pi. R goes from 0 to 1. 2x, I'm going to have 2 r cosine theta, and the 1, that's just 1. And then I'm going to have r dr d theta. Okay, so this is an iterated integral. I'm going to have theta equals 0 to 2 pi. I'm going to do the inner integral first. Okay, so I've got 2r squared. When I take the antiderivative, I'm going to get 2/3 r cubed. When I take the antiderivative, I'm going to get 2/3 r cubed, and I'm going from r equals 0 to 1. So this is just going to be 2/3 cosine theta. And then for the r integral, the antiderivative of r is r squared over 2. And we're going from 0 to 1. So that's just going to be 1/2 d theta. Okay, for the cosine integral, something similar is going to happen as what happened up here. When I take the antiderivative, I'm going to get sine, but sine of 2 pi is equal to sine of 0, and they're both equal to 0. So this integral, that integral is equal to 0. If you don't believe me, just compute it. You'll see exactly what I'm talking about. And so now we're just integrating 1/2 from 0 to 2 pi. So this is equal to 2 pi times 1/2, which is just equal to pi. Which is good because that's what we got when we computed this as a line integral. Okay, so this is what Green's theorem tells us. We are going to be using Green's theorem to convert integrals along the boundary to integrals on the domain. And that's all we have for Green's theorem.